Hello again. I'm going to talk about the Doppler effect. This is the change in frequency of a wave due to the relative motion of an observer and a source. So you've probably experienced this when maybe you've heard a siren approaching you, and as it's coming toward you it sounded higher pitched, and as it passed you and was moving away from you it sounded lower pitched. So what causes that? Well, there are really two causes. It depends on whether the source of the wave is moving or whether the listener or the observer of the wave is moving. So we call it observer because this occurs for all waves. You don't have to just be talking about a sound wave. It could be a light wave or any wave really, and this effect occurs. So here's two cases. Here, case one, I'm saying the source is not moving, but the observer or the listener is. So here's the observer has some velocity, is moving, and here's the source of waves. So this is a sound wave moving out in three-dimensional space, and I've drawn the crest of the wave here. So you can picture this like ripples on a pond. You throw a rock in and the ripples are moving out, but these are now moving out in three-dimensional space, so they're really spheres. And the source is not moving, so these are just moving out in three-dimensional space. But the observer is moving into them, or the listener. So if I head into this, and this is a sound wave, as my ear moves into it, these crests hit my ear more rapidly than if I were not moving. So if they hit more rapidly, the time between the crests is decreased. That means the period is decreased, and therefore the frequency is increased. So I hear a higher pitch. If I turn and go the other way, then the crests are having to keep up with me. There's more time between the crests hitting my ear. Since there'll be more time between the crests hitting my ear, the period is increased, the frequency is decreased, and I hear a lower pitch. Now, that's case one. The source is not moving, but the observer or the listener is. Case two, the observer is not moving, but the source is moving. Now in this case, here I've drawn the situation here. Here I've drawn a wave crest. This wave crest was emitted at an earlier time when the source was here. This wave crest was emitted. This wave crest was emitted when the source was here. So the source was moving this way. This wave crest was emitted when the source was here. This wave crest was emitted when the source was here, because the source is moving toward the observer that way. Notice how the crests are bunching together in the direction of the observer. So that means that the time between the crests will be decreased. So the period is decreased, therefore the frequency is increased. If the observer had been over here, notice the crests are further apart, so the time between them will be increased. That means the period is increased, the frequency is decreased, and so it's a lower pitch. So these are our two cases. Now, how do we handle them mathematically? If I want to derive it, I'm just going to write down the equation and show you how to use it. So you can show the following. The shifted frequency, the Doppler shifted frequency, looks like this. F prime, the shifted frequency, is the original frequency, V plus or minus VO over V plus or minus VS, where the V without a subscript is the velocity of sound in our case. If it were some other wave, it'd be the velocity of whatever the wave is. So this is the speed of sound. So in air, this looks like V is 331 meters per second times the square root of T over 273, T in Kelvin. VO is the velocity of observer or the listener. And VS is the velocity of the source. The thing emitting the wave. I remember this equation myself because O it goes on top, comes before S in the alphabet. The trick is remembering, you have to figure out, you don't memorize, you have to figure out, do I put a plus or minus here, do I put a plus or minus here? And you have to get that on physical understanding of the situation. You have to decide, would the situation cause the frequency to go up or the frequency to go down, and then you put in the sign that causes that effect. So let me show you a couple of examples. Example 1, simple example, and then I'll show you a more complicated example where both the source and the observer are moving. So suppose your violin teacher gets exasperated with you and throws a tuning fork out the window. So teacher throws a tuning fork. She's got a pretty good arm at 22 meters per second. That's 50 miles an hour. Away, so she throws it away from you. So at least she didn't throw it at you. And it's an A. It's a 440 hertz tuning fork. That's the A above middle C on a piano. What do you hear? All right, so F prime is F, V plus or minus V observer over V plus or minus V source. So it depends on the temperature. So we're going to say T is 20 degrees Celsius. So V is 331 meters per second, square root of 273 plus 20 over 273. That gives me 343 meters per second. That's the speed of sound in air on that day. If this were, a problem where you were doing speed of sound in some other material, you'd have to use the speed of sound in that material. VO is the velocity of the observer, so unless you're running away, the VO is 0 in this case. The velocity of the source is the 22 meters a second. Don't say it's minus 22 because it's thrown away. We have to figure out the signs on principles of whether to make the frequency go up or down. So F prime is F, 440 hertz. That's the frequency you get if neither observer or source were moving. It's V, that's the speed of sound, 343 meters per second, plus or minus 0, so we don't care whether it's plus or minus because you're adding 0, over 343 meters per second. These do not cancel because I'm going to add or subtract something to it. Let me make that a little tidier looking. And it's going to be plus or minus V source is 22 meters a second. So I just have to decide whether I put a plus or minus there. Okay, if you throw the fork away, it's going to make the pitch go down. So I need a sign here that makes this smaller. So when I'm dividing by something, dividing by a bigger number makes the outcome smaller. So I'm going to have to put a plus here. Then when I put all those numbers in my calculator, I get 413 hertz, which incidentally is almost A flat, because 415 hertz is A flat. So there's our first example. Example 2. More complicated case. Suppose you're driving down the highway at 50 miles an hour. That's 22.35 meters a second. And you're following an ambulance that's moving in the same direction as you at 80 miles an hour, which is 35.76 meters a second. And it's emitting a frequency of 1200 hertz. That's the frequency the siren emits when the ambulance is sitting still. You know, when they went and bought their siren, it was a 1200 hertz siren. It's on a day when the temperature is 20 degrees C, which implies the velocity of sound is 343 meters per second. We just did that in the problem before. What frequency do you hear? You're in this car, so you're the observer. This is the source. So this is the velocity of the observer. This is the velocity of the source. So we got F prime is F V plus or minus VO over V plus or minus VS. That's 1200 hertz, 343 meters a second, 343 meters a second. The observer is 22.35. The source is 35.76. We have to take these one case at a time. You can't figure out both signs at once. You could, some people sometimes erroneously say, since these are moving apart, because this is going faster than this one, that you can pick the sign based on that one issue. You can't. Because this one is moving toward this one. This effect physically is there, causing the frequency to go up. This one's moving away. That effect is really there, causing the frequency to go down. Both matter, so you have to deal with them one at a time. This one, let's look at this one. The observer is causing the frequency to go up. It's moving toward. That means in this, VO, which we choose a plus or a minus. In the numerator, frequencies go up with a plus here. So that's a plus. In the denominator, we're looking at the source. This is moving away. So that means this, I need to choose the sign that makes the frequency go down. In the denominator, larger values give you smaller results. So this is also a plus. And so the end result is 1158 hertz. All right, well, that's all. We'll practice that in your in-class, in your homework. As always, see you soon.